In this question, you are required to find the Maclaurin series for e to power x squared, and then find the integral of that, and then use that to approximate the value of that integral. So let me start with A. Now, we are going to use the Maclaurin series for e to power x. The Maclaurin series for e to power x is in your formula booklet. Okay, that guy. So then what we'll do is, let me first, so we are going to use Maclaurin series for e to power x. So, and we know that e to power x, the expansion for e to power x will be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And this pattern goes in and we know that the nth term for this, we established this previously in my previous videos, will be x to power n over n factorial, and the pattern goes to infinity. Oh, sorry, the series goes to infinity. So the thing is, by inspecting, you can see that, and by the way, we can represent this as the sum from n is equals to 0. This series can be represented this way. X to power n, so x to power n over n factorial. All right, so this series can be expressed as that. Now what I want you to do is look at these connections. So this is e to power x, remember, but what we want is e to power x squared, which means what you're going to do is to replace x squared in place of x in this series. So what we'll end up with is the expansion for e to power x squared will be equal to the sum from n is equals to 0 to infinity of x squared to power n over n factorial. And this can just be written as the sum from n is equals to 0 when in simplified form, x to power 2n over n factorial. Okay, so A done, and then B, we need to find this guy. So we are integral of that with respect to x. So for B, we need to find the integral of e to power x squared with respect to x, which will be the integral of the sum from n is equals to 0 to infinity x to power 2n over n factorial, and this is with respect to x. Just remember that this can be simplified as take the summation sign out, bring the integral sign inside. You can factor out what doesn't apply when you're integrating. So that will be x to power 2n dx. And this will be equal to the sum from n is equals to 0 to infinity of 1 over n factorial. Now here you can just apply the reverse power rule. So x to power 2n plus 1 over 2n plus 1. And you end up with this expression in simplified form. So x to power 2n plus 1 over n factorial multiplied by 2n plus 1. All right. So for part C, they want us to use the first 4 terms of this series to find an approximate value of this guy. So what you're going to do is we'll produce the first 4 terms of this series. So what you're going to say is, all right, more space here. So the sum from n is equals to 0 to infinity of this series So this is, you know, our series, but we are producing the first 4 terms. You just plug in 0, you'll end up with 1. If you plug in 1, you'll end up with x cubed over 3. If you plug in 2, you'll end up with x to the power 5 over 10. And if you plug in 3, you'll end up with x to the power 7 over 42. And that goes on to infinity, but we just want the first 4 terms. So which means that the integral from 0 to 1 of e to the power x squared dx will be, this is an approximate, remember it's not actual, it's just an approximate. So we know that this bit right, can be represented by this bit, okay? So that bit can be represented, and that's what we have here, all right? So that bit can be represented up here, can be represented by that. So what I'm just going back here, oops, sorry. So the integral, this integral can be represented by that. So what I'm going to do is to plug in those representations in here. 1 plus x cubed over 3 plus x to the power 5 over 10 plus x to the power 7 over 42. And our limits are 0, 1. So in simple words, what you've done is we have basically integrated, all right? This bit, this integral here, all right? This integral here is represented by that, okay? Which is represented by this. And now because we have limits, you just plug in the limits. So what we'll end up with is, 1 plus a third plus 1 over 10 plus 1 over 42. Yeah, 1 over 42. That minus just 0, okay? So if you plug that in your calculator, you should be able to end up with 1.45 714857 as your final answer. Okay. In this question, we are required to find the Maclaurin series for f of x is equals to x cos 2x. So what you're going to do is we shall use the Maclaurin series expansion for cos x, and this is in the formula booklet. All right, so cos x is given by that, and we can just put it down here. So cos x is given by 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial plus whatever comes next. And we can, previously we discussed this in my previous video. I mentioned this, and I showed you how you can come up with a formula for this. And the formula was negative 1 to power n, starting from n is equals to 0, x to power 2n over 2n factorial. All right, remember this is n is equals to 0, n is equals to 1, n is equals to 2, n is equals to 3. And you can just use that pattern to kind of, the powers of x are even powers, the factorials are even powers starting from 0 factorial. Okay, now, and then this goes up to infinity. Anyway, back to the story. So, cos x can be represented by this series. So you can write this now that we have the formula for nth term, s sub n. We can plug it here. So negative 1 to power n x to power 2n over 2n factorial. Okay? Now, this is a series that represents cos x. But what we want is cos 2x. So what I'm going to do is just to write here cos 2x will be, we'll plug 2x in place of x, which means I'll end up with sum from n is equals to 0 to infinity, negative 1 to power n, 2x to power 2n over 2n factorial, which can be simplified as sum from n is equals to 0 to infinity, negative 1 to power n, 2 to power 2n, x to power 2n over 2n factorial. This will be equal to the sum from n is equals to 0 to infinity, and then we can have negative 1 to power n, 4 to power n, x to power 2n over 2n factorial. So we have the expression for the expansion for cos 2x. Now what we want is x cos 2x. So hence the expansion for x cos 2x will be equal to x multiplied by this series. All right, so negative 1 to power n, 4 to power n, x to power 2n over 2n factorial. And that will be equal to the sum from n is equals to 0 to infinity, negative 1 to power n, 4 to power n, x to power 2n plus 1 over 2n